Alright, so this video is actually going to go through an actual calculation of the projectile launcher lab. So what I'm going to do is the last video actually went through like the algebraic manipulation, so this is going to be an example walkthrough so you can use it to go through kind of with your own numbers. But essentially, step one of the lab, which I talked about in the last video, why, is I go through and I launch this projectile straight horizontal and then it hits the ground. And the only thing that I have to really measure is this delta x right here. And then of course I'm also going to measure the height that this is at relative to the ground. So for this example, my height relative to the ground, which is right where the projectile comes out of the launcher, was 1.22 meters. And then the displacement that it underwent was 2.49 meters. So those are the only two things that I actually really need to measure in order to start everything. Everything else on this lab is completely based off of one measurement, and that's this one right here, with the way I did it. And of course this one right here, this is kind of background information, but this is something I measure. This is something that's actually experimentally measured, so that's going to be the one thing that every single thing in this lab comes down to. So for this one, my first step, well, delta x equals the velocity in the x direction times the time, and I'm looking for the velocity in the x direction. So the velocity in the x direction equals delta x over t. And the reason I'm looking for the velocity in the x direction is because when I'm firing this straight horizontal, that is my cannon's velocity. So that's going to be the velocity at any angle, regardless of what the angle is. So I can go ahead and I can plug that in, and my delta x was 2.49 meters. And my time is the only thing that I have to calculate my time. So there's potential for round off error, but this is very minimal round off error. So my time in the air is completely dependent on the y direction. The y direction, my y initial, sorry, let me undo that here. My y initial is going to be that 1.22 meters. My y final is going to be 0 meters because that's going to be on the ground. A equals g equals negative 9.8 meters per second squared. And I'm looking for t. Now I'm going to use my, with this given information, oh, and the other thing is, because this is shot straight horizontally, VIY is 0. There is no initial velocity in the y direction. So what I'm going to use then is going to be my YF equals YI plus VIT, and that's the VI in the y direction, plus 1/2 AT squared. That's my formula because I have everything. So let me rewrite that real quick. Alright, so there's my equation. So again, looking at this, YF equals YI plus VIY, T plus 1/2 AT squared. So looking at that, VIY is 0, so this whole term goes away. YF is 0, so that term goes away. And if I rearrange this and solve for time, I get my special case equation that we've already talked about, where time equals the square root of negative 2yi over g, and g is a is g, however you want to think about it. So if I plug that in, I get negative 2 times my yi. My yi was the 1.22 meters. And I'm going to divide that by g, which is negative 9.8 meters per second squared. And then I'm going to take the square root of that, and I got 0.4989 seconds. 0.4989 seconds. Now I'm keeping a ton of sig figs just to kind of try to eliminate some round off. I'm not justified for these, but I will go through and use them just for the time being. So this time that's right here is what I want to plug in for the time right here. So if I take my delta x, which is 2.49 meters, and I'm actually what I actually do is I'm not going to clear this from my calculator, and I'm going to use the calculated answer that my calculator gave me, and then eliminate as much possible round off error. And I got 4.99, and that's going to be my Vx, so that's going to be 4.990 meters per second, or 4.99 meters per second. And I actually happen to know that that's about right, because the projectile launchers, this is at 2 clicks, have about a velocity of about 5 meters per second. So I'm going to get this kind of cleared up, and we'll go into part 2. Alright, so I cleared off my screen a little bit, and now I'm on to the second part, and I pointed out that the velocity of my launcher, or my projectile launcher, is 4.99 meters per second. Now it's 4.99 meters per second regardless of what angle it's at. That is just 4.99 meters per second. So in part 2, I still start with the same 1.2 meters firing it up, but now it's going up at some angle, and it's going some distance, and it's going to land. And now, because it's going up at some angle, it's going to land further than what it did initially, so my delta x is going to be slightly different. But my formula stays the same. The delta x still equals the velocity in the x direction times the time. So my first step that I'm going to do is I'm going to break my velocity into components. And I'm going to do that over here on the side. So my velocity is 4.99 meters per second. And for this example, my angle is going to be 25 degrees. So I would put that 25 degrees right there. So if I'm looking for Vx and Vy, I'm going to use cosine for Vx, and I'm going to use sine for Vy. And so if I plug into my calculator 4.99 times the cosine of 25, I get 4.522 meters per second, and that's going to be my velocity in the x direction. And if I plug in my velocity in the y direction, that's going to be 4.99 times the sine of 25, and that's going to give me 2.109 meters per second. And just a reminder, that's my initial velocity in the y direction, and of course I'm going to undergo acceleration due to gravity, so that's going to change. So on my right hand side over here, I have all of my velocities. I have the velocity of the launch, velocity in the x direction, and the velocity in the y direction. Now going back to this equation down here, I use the velocity in the x direction, and I multiply it by my time to figure out how long it's in the air. But my time is 2 chunks. It takes me the time to go up and the time to go down. That's how I'm going to break it up. I feel like that's the easiest way to break it up. So there's t up and t down. Now t up is pretty easy because t up is just the time that it takes me to go from my initial y velocity to 0 y velocity with the acceleration of negative 9.8 meters per second squared. So for that formula, it's Vf equals Vi plus At. Vf is going to be 0, so I'm going to get rid of that. And then I have negative Vi over A equals T. So that equals negative, Vi is 2.109 meters per second. And G, or A is G, which is negative 9.80 meters per second squared. And if I plug that into my calculator, I get negative 2.109 divided by negative 9.8, and I get 0.215 seconds. So T up is going to be 0.215 seconds. Alright, so that gives me half of my problem. But now I'm worried about the time that it takes to go down. And just like I did in the first part, I can use my special case equation for that. But in order for me to do that, I need the new height that's right here. So the object went up, and now it's going to go all the way down. So my special case, I need to account for this side. It's got to go up right here. And it's going to go up by delta y. Because this was the initial y. This is my new initial y. So it went up by delta y. So I need to figure out what exactly that delta y was, or is. And so the way I'm going to solve this is I'm going to use Vf squared equals Vi squared plus 2G, G is A, delta y. and I'm solving for delta y. And VF, of course, is going to be 0. So I have negative VI squared divided by 2G equals delta y. And if I plug that in, I have negative, again, 2.109 meters per second. That quantity is squared, divided by 2 times negative 9.80 meters per second squared. So that delta y, and that's how much I've increased. So it's not my new height, it's just how much I've increased. That is going to be, if I plug that in, 0.227 meters. And that's about all I'm going to be accurate about. So delta y equals 0.227 meters. And that means that if I take my 1.22 meters that I already had, I'm going to add 0.227 meters, and that's going to be my new height. So now, coming from the way down, my 0.227 plus 1.22, my new height is 1.447 meters. So that is my new height for the second half using time down. Alright, so my next step is to solve for the time down, and using my special case equation, I know that time down equals the square root of negative 2yi over g. So if I go ahead and plug that in, I have the square root of negative 2 times my yi, which is my new yi, which is 1.447 meters, divided by g, which is going to be negative 9.80 meters per second squared. And if I plug that into my calculator, I get, divided by 9.8, take the square root of that, I get 0.543 seconds. So t equals 0.543 seconds. So that is my time down, 0.543 seconds. Alright, so that's that. That's it for my time down. Now, a special thing that I want to point out right here is if I was to take into account the height of the cup, I cannot do my special case equation. That is only true when y final equals 0. So in this case, I used it, but that means that I'm not accounting for the height of the cup. But that's going to be probably close to within the spectrum of experimental error anyway, and I don't want to have to confuse it by adding that. So for all our intents and purposes, we're just going into the ground level. And our very last step is that our delta x equals Vx times t. Well, our Vx is going to be 4.522 meters per second. My t is going to be the 0.215 plus the 0.543. It's the combination of those two times. It's the combination of time up and time down that gets me my total time. So I'm going to go ahead and plug that into my calculator. So 0.215 plus 0.543, and I got a total displacement of 3.427 meters. So delta x equals 3.427 meters. So that's it. That's how far I need my projectile is going to land from the base of where it was fired when it is done getting fired. So that is it for that problem. Yeah, if you have any other questions, you should definitely check the other video that goes through it a little bit more conceptually. Otherwise, that is how you solve the projectile launcher problem.